So hello everyone again to this 2024 IEEE online forum on climate change technologies. Thank you all for participating in this event. I would request all of you to keep your microphone muted when you are not speaking and turn off your videos if not presenting. For your information, copies of this presentation will not be shared. Instead, check back later the OFCCT website for on-demand recordings for each session. Please submit your questions and comments via the chat box. And with this, I would like to introduce our next speaker, Dr. Marios Sophocleus. Pardon my pronunciation.
Sophocleus, no worries.
Okay, thank you. So Dr. Mario is an esteemed researcher and expert in agri-food electronics and sensor technology, holds a PhD in engineering with a focus on thick film underground sensors, complemented by a master's of engineering in mechanical engineering, mechatronics, from the University of Southampton, UK. His academic journey commenced with roles as a research scholar and postdoctoral research fellow at the University of Cyprus, where he concentrated on soil quality monitoring technologies for the agri-food sector. Currently, he assumes the position of Senior Project Manager and Head of Electronics and Beyond 5G Testbed at eBOS Technologies Limited, Cyprus. In this capacity, he supervises the progress of over 10 EU projects, manages hardware acquisitions, and lead both the electronics team and the B5G testbed, actively contributing to novel EU proposals. Additionally, Dr. Marios enriches his research endeavors as a visiting researcher at Tel Aviv University, engaging in collaborative efforts focused on plant monitoring technologies. Dr. Marios' commitment to advancing agri-food electronics and sensor technology resonates through his prolific scientific contribution. He has authored numerous publications, including papers on sensor technology and precision agriculture, featured in esteemed journals like IEEE Sensors Journal and Biosensors and Bioelectronics. His influence extends to the IEEE Transaction on Agri-Food Electronics Journal, being a founding member of the steering committee, and an associate editor, and the IEEE Conference on Agri-Food Electronics, being a member of the organizing committee in 2023 and a general co-chair in 2024, where he actively shapes the technology landscape of agriculture and food production. Furthermore, he has edited books, penned books chapters, and authored magazine articles on subjects such as IoT and thick film technology for agriculture. His exceptional contribution have generated recognition, including the Fulbright Schumann Award and finalist status of the Cyprus Young Scientist Award. With this, I would like to invite Dr. Marios for his presentation. So Marios, this platform is all yours.
Thank you, Mr. Thank you very much. In my capacity today, I'm also the co-founder and managing director of TerraTech Innovation, which essentially is the startup that is focusing on commercializing the work we did on soil sensing and both the sensors and the sensing system with electronics to go along with it. Today I'll be presenting I have a presentation of advanced in-situ technologies for real-time soil quality monitoring. And the objective here is to explain and unveil the connection between soil health and climate stability. So I will start with explaining the connections between soil health and how it connects to the climate, and that how the soil health has been under pressure in this century, essentially the last 10 years, and keeps increasing because of agricultural practices, decreases of arable land. We'll see those challenges later. Then I'll move on to explain how we assess soil quality and essentially describe the soil quality indicators. And I'll give an overview of the conventional soil sensing technologies, then explain the work we did with TerraTech with in-situ sensing technologies, and then the benefits of using real-time data on decision-making for soil health and eventually its effect on the climate. And then I'll just give a brief conclusion on future directions where we think that the next technologies in soil quality monitoring will be. Okay, so starting from the importance of soil health, climate and soil are mutually interdependent. So there's a bidirectional relationship between the two. Soil acts as a climate regulator or a carbon sink. The mechanism for that is that plants will absorb carbon dioxide through photosynthesis and transfer carbon through the roots down to the soil. Eventually, soils can store about 2.5 thousand gigatons of carbon, which is more than 3 times the amount in the atmosphere and over 4 times the amount in vegetation. So the capability of soil of absorbing carbon significantly affects the climate and the overall climate change. Other than looking specifically only to carbon, soil also affects the water cycle, and it regulates the water cycle because if the soil is healthy, it can absorb and store water, it can recharge groundwater, it filters the water that goes through the ground, essentially allowing for a cleaner and better quality groundwater. It reduces the surface runoff and essentially stabilizes the humidity and temperature of the climate. Now, when the soil is not healthy, the release of carbon dioxide, because the soil cannot absorb and maintain that carbon dioxide in the soil, the carbon dioxide evaporates and goes back to the atmosphere. Also, methane, nitrous dioxide, due to accelerated decomposition and distributed microbial activity. So we'll see a bit later on the relationship, how that happens. Now, when organic matter decomposes, it releases CO2, and when the soil is extremely wet, and it also releases methane and nitrous dioxide. So essentially, there is a feedback loop here. The soil affects the climate, and then climate affects back the soil. So there's a chain reaction and a continuous loop. So ensuring that soil quality and maintaining soil quality can significantly stabilize the climate. Now, rising temperatures from the climate, again, as a result of global warming and the greenhouse gases, it also affects the soil by increasing the microbial activity, which accelerates the breakdown of the organic matter. Again, as the soil loses organic matter because of the higher temperature and the accelerated decomposition, then the carbon holding capacity declines, again, pulling back to the same loop. So when there's intense rains, the soil can erode. We have seen many landslides, we've seen many soil tillage issues, even recently with the effects in Valencia, but essentially this flooding and erosion can affect climate change, and because of climate change, we have those effects. Now, other than just the chemical content of soil and its ability, the biodiversity within the soil can also affect the decomposition of organic content, which affects plants, which affect, again, the climate, and back to the same loop. Now, what is the conventional ways of monitoring soil quality? We usually use monitoring through soil sampling, but this is only on rare occasions. Like you have specific time intervals that is required for you to go and take some samples and run the tests. However, this essentially limits the prediction and proactiveness. So we need a different technology and different technologies so that we can be a bit more proactive than reactive in these cases. Also, in order to make decisions, we need data-driven decisions. So this real-time monitoring technologies for the soil quality can provide very useful insights on how to control and maintain soil quality and soil stability. So what are the main challenges for the soil? Where does that need come from? Population growth is one of the challenges. It has been predicted by the Food and Agriculture Organization by 2050 you have about 10 billion people, which increases the need for food. So in order to provide more food, we need more agriculture to produce more. But at the same time, we have the decrease in arable land. So the amount of land that we have in order to generate produce decreases. Hence, the only way of achieving higher production with less amount of land is by increasing the efficiency of agriculture. However, this puts a lot of pressure on the soil. It puts a lot of pressure on the environment in general. So unsustainable farming practices degrade soil. One of the things that usually happens is obviously the rapid urbanization and the soil degradation affects these practices. But again, the effects of current agricultural practices and uncontrolled and unmonitored agricultural practices have a significant effect on soil quality. For example, the soil organic matter, as explained before, is one of the key parameters that affect soil stability, and eventually that soil stability affects the climate. One of the parameters that significantly have an issue here is the use of water. Obviously, when you over irrigate your fields or you're under irrigating your fields, it has a significant effect on the quality. But one of the things that we see and we keep increasingly seeing is the use of pesticides and fertilizers. So with the pressure of producing more, with more efficiency and higher quality fruits, or maybe higher nutrient fruits, the provision of fertilizers significantly increases, and up to a point we are actually using more fertilizers that are possibly needed for the specific plants or specific vegetables that are needed. Also, the use of pesticides to eliminate any insects or any other potential harmful living organisms on the plants have also an effect on soil, because it changes the ecosystem, it changes the chain, how soil maintains its health and essentially the soil organic matter inside the soil. There are ways of ensuring climate resilience and sustainable soil management, which involves, for example, crop rotation and cover cropping. We've got reduced tillage, the use of biochar or organic amendments, reforestation and agroforestry. And for all of those things, the United Nations came up with sustainable decisions, goals, which emphasize on soil restoration and ensuring the quality of the soil and the fertility of the soil in order to avoid the negative effects that soil quality, the poor soil quality has on the climate, and vice versa. Now, we mentioned about soil quality, and we need to maintain that soil quality. In order to do that, we need to understand how do we do that. So usually we have in an engineering problem, we've got inputs, we've got outputs, we've got processing points, this essentially is an optimization problem. But in order to understand the problem and optimize this problem, we need some information, we need some data. And currently the technologies that we have are not enough to define essentially the transfer function, if you want to think of it as a transfer function of the soil with the inputs and the outputs. The reason for that is back in the day and so far, we assume that soil doesn't change so quickly. We assume that soil parameters are significantly stable. However, recent studies have shown that plants are essentially affected by all parameters in the soil. Even the temperature, even the time has an effect on when you're watering the plants or when you're fertilizing the plants. So we need some kind of a dynamic 4 dimensions connection between the soil, the plants, and eventually the climate. So what are these parameters? How do we optimize for that? What do we need to optimize? Soil has been described many years ago, about 30 years ago, that it's the most vital component for food and fiber production. And these essentially led to the definition of the soil quality indicators, and which correlate well with ecosystem processes. They integrate several other processes. They can understand how the mechanisms, they are good indicators of the mechanisms happening inside the soil. And they define them as 3 different categories: the chemical, physical, and biological soil quality indicators. We'll see these in a bit more detail. So if you're going into physical indicators, they will give you information about soil hydrologic characteristics, so water entry and retention. As we explained before, this affects the water cycle. Then those soil hydrologic characteristics can also give you information on the nutrient availability and the erosion status. Furthermore, these indicators also include the aggregate stability, water capacity, bulk density, infiltration, slugging, soil crust, and soil structure, and micropores. This is one of the categories that we use as soil quality indicators. The other one is the chemical soil quality indicators, where most of these affect essentially have a direct effect on the essentially the mechanisms that affects the microbiological organisms inside the soil and the plants, how plants absorb these nutrients in order to grow. So those soil chemical content establishes the equilibrium between the soil solution when you have water and the rest of the biodiversity inside the soil. You've got the plant health and nutritional requirements of plants, and all of those things are essentially variable. So depending on the type of plant or depending on the type of soil for the same plant, those things can change and the optimal points could be different. Also, as I explained before, even the time can affect the quality of the produce. I attended one of the conferences, and one of the plant scientists, he mentioned specifically that depending on the time that you water the plant, you can enhance either the production of fruits or the production of sugar that is stored in the fruits, or you can actually enhance the growth of the plant just by changing the watering time. Some other indicators here include the electrical conductivity of the soil, the nutrient concentrations, the micronutrient concentrations. These micronutrient concentrations, for example, other than just for plants, they can also be used for understanding how well the soil keeps together. So the balance between sodium and magnesium and calcium can tell you how well the soil sticks together. So you can predict and understand any erosion issues and predict that. Now, going on to biological indicators, obviously the amount and the culture size of some bacteria in the soil or some other organisms in the soil is vital. But other than the amount of organisms in the soil, the type and the diversity of those organisms in the soil are also important. So eliminating one of them can cause a chain reaction, a negative chain reaction to all of the rest. So some of those indicators involve earthworms, particulate organic matter, potentially mineralizable nitrogen, soil enzymes, and total organic carbon. Now, how do we measure these soil quality indicators? We measure them using the standard conventional soil sensing technologies involve soil sampling, as I said before, but this requires significant steps, and they require a very well-trained personnel to go and pick that up, because if something does not follow the specific procedures from soil sampling to transportation or to preparation, then the overall measurement is unreliable. So some other techniques that are actually used on sites to measure soil. Most of these things do not measure soil chemical content, but most of them are for physical soil quality indicators. Those involve the standard penetration, the cone penetration, dilatometers, pressure meters, veins. There's a lot of equipment that is actually being used for this kind of soil quality indicators. However, they are not standalone or real time. So you have to go there, take the measurement and leave, or you can go leave it there, but every time you have to go and check. So there is another option for the mostly chemical soil quality indicators, which involve soil chemical analysis kits. But again, you have to go to the field, take the samples, and you can actually run these tests in the field. Again, they require trained personnel, a human presence, and they cannot give you continuous data. Looking into the current state of the art for soil monitoring, we've got two main categories here. We've got the remote sensing, which has grown very much in the last decade. We've got satellite imaging, which you can do multispectral images. You can understand even the soil chemical content at the surface of the soil can be identified. We also have unmanned aerial vehicles who can do the same. They can even do soil sampling. On the other side, we've got actual soil sensors. There are two main categories here. Okay, there are more types of sensors, but I think these categories cover the big majority of them. On-the-go sensing systems are essentially sensors installed on agricultural equipment like tractors. So every time that the equipment goes through the field, it also takes measurements from the field. And the last category is the in-situ soil sensors. So essentially you deploy these sensors in the field and you receive data in real time. Those conventional techniques, most of them require soil sampling, excluding the ones I just mentioned. If you go back to the previous slide, most of them require soil sampling, but the latest one also require, maybe there is no human presence in that case, but the sampling frequency is not as good as expected. Even for the satellites, you can get an image every time the satellite goes above the specific field. With the aerial vehicles, you have to send it and then send it again, which needs to come back and recharge. So what is really needed is the in-situ and standalone continuous and autonomous soil sensing system for this to understand all of the parameters that affect the soil quality. Some of the existing in-situ soil sensors are effectively monitoring. You can see here the list of some electromagnetic sensors monitoring mostly impedance, or some radioactive techniques, or spectrometries, or X-rays, or calorimeters, and the remote sensing technologies explained before. The main, in reality, the only ones that are standalone and in situ, and you can take continuous measurements, and they're all the ones that are available at the moment, is monitoring the impedance of the soil, from which you can detect soil water content if you're looking at impedance at higher frequencies, and soil conductivity, or which corresponds to soil salinity if you're looking at lower frequencies. But still, these are either very expensive or they are not reliable with a very short lifetime. Now, from TerraTech, what we proposed and what was the starting point was we wanted to replace this and design and come up with a solution that can be installed in the soil and stay there and take measurements for a long period of time. So what we used was to transform some existing sensing technologies from the macro scale to screen printed solid state sensors, and then find a way of a technique to deploy those sensors in the field and take the measurements. Now, why thick film technology? It gives you a lot of flexibility with the design. You have a lot of materials to choose from. It's robust and they are reliable. They can operate in harsh environments. They integrate very well with electronics, significantly low cost, and they allow miniaturization and lab-on-chip compatibility. This is just one prototype that we have. We can see the sensors that we have on the one side and the back side of a substrate. These are printed on alumina substrates. On the left side, you've got the impedance measurements, so it can detect the water content and salinity. On the right side, you've got a thermometer, a pH sensor, a potassium, and a nitrate sensor. This is the size is about 5 by 5 centimeters for the whole system, and if you mass produce it, the cost should be, and I'm talking about the fabrication cost, should cost about 20 euros. Now, the overall design that we use and the approach that we're using here at TerraTech is that we place the sensor below the surface of the soil. We've got the electronic system on top of the above ground. When you verticate, the water goes through our package. It goes to the sensors take the measurement, and then the water goes out from the package. Now, the idea here is that the fertigation, you're sending water that with unknown concentrations, then some of those minerals are absorbed by the soil, and then you're measuring, and you can see the difference between what you provided and what you measured, so you can estimate at least what has been absorbed by the soil. This is just an interesting concept of what we're doing. We've got multiple holes here, going the water in and then providing the water down to the sensors. The sensors, the whole package has a Pythagoras cap, so once it reaches above a certain level, the water empties, which allows to essentially improves and enhances the lifetime of the sensors because they're not always in the water. We developed that. We printed that. We also designed all of the electronics for that, and we came up with a prototype that we have based on a completely standalone system, as you can see on the left, and on the right with the electronics. This is a complete prototype, as you can see, and the prototype has been deployed and tested both. I mean, this is just an example in a pod, but we're also deploying the sensor and the sensing system in the field. From those tests, we managed to get some very useful results because we can see that after watering and during watering, we can identify essentially the changes that we expected to see, both in terms of impedance, also in terms of potassium and nitrate concentration, as well as pH. Now, what is the benefit? I think the benefit of using real-time data and real-time monitoring is to allow to understand. It gives us all the information we need to understand how soil and essentially all of those soil quality indicators can affect soil health, and eventually how that component affects the climate. Also, of course, this will give us the interaction and the possible mechanism between how these parameters are correlated with the carbon sequestration, and devise and understand the actual mechanism and define that mechanism so that we can know what are the optimum points. So what is the goal here is to understand again the soil variability, and since those soil properties fluctuate with climate conditions, other than just having optimum points without taking into account the environmental and climate effects, monitoring all of those things together as a complete system with inputs and outputs, this allows to fully define the overall mechanism. And further, it allows the adaptive management, so we know how to react and what are the correct mitigation measures that we will need to take in order to ensure sustainable climate and sustainable soil quality. Again, with this type of sensors, we can see the greenhouse gases emissions and have targeted interventions specifically in the for each region. Again, based on the Sustainable Development Goals coming from the United Nations, there are specific goals for soil quality monitoring. So this has been identified also by the United Nations and the Food and Agriculture Organization. So these kind of systems are actually requested and are actually needed. So my personal expectations is that these kind of policies and these kind of solutions will be eventually put in place to ensure the correct fertilization and irrigation uses. Now, what are the future directions we expect? We expect to see artificial intelligence and machine learning. In order to use AI and machine learning, you need data. So using these kind of systems, we expect to provide more data than what we actually have and devise more accurate and more specific algorithms for predictions and even real-time decision making. Also, we expect to see more innovation and a lot of work to be done in sensor innovation, but specifically how to deploy this kind of sensors. I mean, monitoring the specific nutrients that we were discussing and the specific components the soil has in the lab has been done before, but the implementation of those sensors in the soil has still been not achieved yet. So maybe we'll end up with expanding also the soil health indicators. And one of the other points that we expect to see is the inclusion of new sensors in biological monitoring. I personally haven't seen any biosensors being deployed in the soil yet, but since the biological quality indicators are of high importance, I expect that work will come in this direction. Also, we'll see carbon sensors in the soil. Again, I haven't seen any total organic carbon or sensors for total organic carbon deployed in the soil directly or above the soil for this one. But using all of those things, we expect to see the implementation eventually of precision agriculture, ensuring a more sustainable soil maintenance and soil quality monitoring. Now, just to conclude, the soil is one of the fundamental components of the climate sustainability and climate stability, since it plays a critical role as a carbon sink. In order to understand all of those mechanisms in the 4 dimensions of XYZ and the time, we need more real-time monitoring, and essentially the key takeaways is that we expect to see immediate action in investing in soil monitoring technologies and in order to meet the climate and sustainable development goals. So this is from my side. Thank you very much. I hope I stayed within the time.
Yeah, thank you, Ayos. Thank you for this very interesting talk. Now we will take questions from the audience. We already have a few in the chat box, so I'll read that out for you. So the first question is from Charles. So regenerative farming talks about carbon sequestration and that it increases the carbon in the soil. Can you say
Yes.
more about how carbon in soil is measured? And can electronic sensors be developed or improved?
Quick question is, I haven't seen any sensor that is currently deployed in situ and can provide real-time data on the total organic carbon in the soil. Most of those things are actually measured using either field test, like the kits that I've shown before, or either by soil sampling and taking them to the lab. But I expect that work is coming in this direction because it's a very important quality indicator.
Mhm. So is there a way to improve those sensors or to develop those sensors if you have any idea on that?
You mean Terratech sensors or in general the soil sensors?
No, I mean, for example, if somebody wants to make a carbon sensor that can detect carbon in the soil,
Um,
or maybe sensors
well,
in general.
there are techniques that are being used in the lab, but they usually involve they're pricey, they're expensive and complicated. So I mean, maybe there is a way to like in terms of technology and science, maybe there is a way to deploy this kind of sensors in the field, but the problem is the economic side of it. There's no way you can convince a farmer to install a sensor that costs, I don't know, 15,000 euros to measure the total organic carbon. So there should be a trade-off between the two there. And I think this is what's causing the delay in the deployment of these sensors.
I see. I see. So we have another question from Saiban. So how to scale up this sensor system to a larger agricultural field? So is there a way to scale that up for larger?
In terms of our side, I mean, in terms of Terratech, you can deploy as many sensors as you like. The system that we have communicates with multiple technologies, even LoRa, so you can set your own private network. They can talk to each other, so they can exchange information. And all of these things, in our case, we connected our systems to an online platform, and we can send the information and visualize the information online. So you can even do multiple hopping between the devices if you like. So yeah, you can extend it as much as the technologies allow you.
Mhm. So I think Charlie has another query, which is a follow-up to the previous one. So how about remote sensing in this area? I mean, you already have said how we can improve or develop similar sensors, but what about this remote sensing concept in this?
I mentioned remote sensing before, and what is usually used for remote sensing is either satellite imaging or taking images through unmanned aerial vehicles or something like that. So that can give you information about the surface, the soil surface, but it cannot give you information under the surface. And again, it doesn't give you continuous measurements. It will give you whenever you send or you request that information from that. So if you're looking at a four-dimensional and then dynamic understanding of the mechanism, then there are some difficulties there because you are missing data.
Yeah, I see. So Saivan again has another question. What is the expected service lifetime of these sensors? And how, I mean, there is another question. I'm saying it together.
Okay.
Is the sensor system designed to be biodegradable because it's related to soil, maybe?
At this stage, we didn't dive into the biodegradability, but what we printed was just to prove the concept and have a prototype, and that's what we managed to do. But yes, eventually you can use materials that are biodegradable. I think the next speaker is going to specifically mention that. About how to use electronic and conductive materials that are biocompatible and biodegradable, essentially having a sustainable electronics approach. In our case, we didn't dive into that direction yet, but it's within our plans, at least in the next couple of years.
I see. So any comment on the service lifetime of those sensors?
Oh yeah, sorry. The sensors that we're using right now, usually thick film sensors, when you have them on the shelf, they can have several years of lifetime. When you use them in the field, I expect to be a couple of months at this stage, at least. Of course, you can extend the lifetime with further enhancements, but with the prototype that we currently have, we're talking about a few months.
I see. Nice. So we have another very interesting question. So what can I do to increase my garden as a carbon sink? So it's like a kind of question that requires some sort of plan.
Okay.
So comment on that.
Okay, it's not an easy question, because soil acting as a carbon sink is just a mechanism that soil essentially can do. But ensuring soil quality, then you can use soil as a soil carbon sink. Now, what are the optimal points on the soil quality indicators to improve the quality of soil as a carbon sink? That's a completely different question, and I honestly don't have an answer for that. That's why we need the systems to monitor and take data and identify what those optimal points are.
I see. Yeah, I see. So one more question is, what other sensors we can develop or we can improve in order to take these soil measurements and stuff like that?
Well, okay, NPK sensors are obviously the most important nutrients, so that's what we started with. But sodium, we also did some work with screen printed sodium sensors. We did some work with magnesium sensors as well. Those parameters affect erosion, so this kind of parameters are also important. Looking into micronutrients, maybe iron or zinc. And if you want to look into soil pollution, then you have to go to heavy metals, and that's a new, I think it's a different field. But in that direction, actually, there has been a lot of work for making sensors for heavy metals in the soil. But again, they develop the sensors and run the tests in the lab. I haven't seen anything being deployed directly in the soil.
Nice. So I have a follow-up question to that. So which type of sensor do you think is the most important one as far as the soil quality is concerned? Because you have mentioned a few.
Well, it depends on the application. It depends on what are you trying to detect. First, you should go the other way around. So I want to optimize for this thing, for this application. For that application, the most important soil quality indicator is this one. Then you need a sensor for that soil quality indicator.
I see. And how about the cost implication? For example, if somebody has a very large field and then they want to deploy these sensors throughout the field, so can you give us a cost implication of this type of deployment?
Yeah, this is what I mentioned, what I meant before when you asked me about the total organic carbon sensors. So, I mean, in our case, as a goal, I would say as a goal, you should talk about something like each sensor system should be about, I don't know, less than 100 euros or something like that. And depending on the field, then you would need to use different amounts of soil sensors depending on how much the soil changes in terms of soil structure or soil type within the same field. So it's not a clear-cut question and answer here, because it really depends on the specific field, and it also depends on the plants and the vegetation that you want to grow. If you're looking about vegetables which respond very quickly to variations in soil, soil quality indicators, then you will need definitely more sensing systems. If you're talking about trees, large trees like I don't know, oranges, lemons, or anything like that, then the need is not that high.
Yeah, okay, I see. I see. So we have another question now in the chat box. So is there any sensor for detecting and measuring the minerals of the soil?
What minerals? I mean, okay, all of them are minerals, but I mean, you're looking about NPK, those are minerals. You're looking about, I don't know, sodium, magnesium, calcium, all of those are minerals, but I'm not sure which mineral you're talking about.
Yeah, I think it's NPK is the very popular one because which is related.
Yes,
Plant.
NPK is the most popular one because it's actually the fertilizers that you're using in agriculture. But if we switch a bit to climate, then it's not just NPK. NPK is used for the plants, but for example, heavy metals can significantly affect the quality of groundwater and the pollution within groundwater. So it depends on the application, which side of the coin you're looking at.
Yeah, right. That's true. So I think with this we have completed the questions that are there in the chat box.
Okay,
But
thank you.
minutes before we start the next session, but I'd like to thank you, Marius, for
Thank you.
this wonderful talk.
Thank you for the invitation.